video, we will see the generation of Soliton pulses and also the evaluation of the Soliton transmission performance using sample mode in OptSim. This schematic shows two ways to generate a Soliton pulse. In the first schematic, the Soliton pulses are generated by applying an RZ Soliton shape electrical driver to a linear amplitude modulator. The second schematic uses an optical pulse generator model under optical sources to directly generate the Soliton optical pulses. You can find all the models used in the schematic from the all models, sample mode models. Here under logical source, you can find the data source, you can find the NRZ driver that is used in this case, and you can find the race cosine Soliton driver here, which is used in the first schematic. Under optical sources, you can find the CW laser source as well as you can find the Soliton optical pulse generator that is used in the second schematic. Under optical modulators, you can find the linear amplitude modulator, which is an external linear amplitude modulator. Under split and combine, you can find the optical splitters. Under photodetectors, you can find the pin photodiode. And you can get all the measurement components from the measurement component section. You can drag and drop these components into the design area and make the connections as per the schematic. So here we are using a laser source of 1550 nanometer, and here we are using an RZ Soliton shape electrical driver. So in the driver you can mention the voltage level as well as the FWHM resulting through the linear modulator, and the linear amplitude modulator loss is taken as 3 dB. In the second schematic, we are using an Soliton pulse generator to directly generate the optical Soliton pulses. So going to the properties of that particular block, we can set this center emission wavelength as 1550. You can choose the laser phase. The time between two pulses is taken as 1000. You can mention the full width half maximum value and the peak power. Once the connections are made and properties are set, you can run a simulation. Click onto the go button and start the single run. Once the simulation is complete, let's take a look at the Soliton signal. So here this is the Soliton signal that was generated using the first method, and here you can find the Soliton signal that was generated using the Soliton pulse generator model that is available in OptSim. In this particular schematic, we will analyze the performance of a Soliton transmission over an optical link. Here the Soliton pulses are generated using a Soliton pulse generator as an optical source, and then it is modulated by an external linear amplitude modulator which is driven by an NRZ signal. The fiber link here has multiple span, for which we have used OptSim iteration loop. So if you just go to the properties of the loop, you can see that number of repetitions is 20 spans of fiber be included in this design. If you just go to the look inside option of the loop, here we have an optical fiber and an inline EDFA. The fiber length for a single span is taken as 50 km. Loss is taken as 0.2. Dispersion has a value of 1.56 picoseconds per nanometer per kilometer. And the inline EDFA gain shape is chosen as flat and the gain is taken as 10 dB. So this constitutes a single span, and within the loop we have 20 such spans. Here we have added two receiver sections basically to see the transmitted pulse as well as the received pulse. If you go to the properties of the Soliton pulse generator, the center emission wavelength is taken as 1550 nanometer. The laser phase is taken as deterministic and the initial laser phase 0 and time between two pulses is taken as 200, and the full width half maximum is taken as 17.6 picoseconds. Peak power of the Soliton pulse generator is taken as 25.58 milliwatt and average power as 1.27 milliwatt. So here a 5 gigabits per second Soliton signal is launched into the 20 span of fiber, each of 50 kilometer length. So we can just run the simulation. Once simulation is complete, you can compare the transmitted and the received signal. So let's open the electrical signal, which is the transmitted electrical signal, and also the received electrical signal. You can compare both the signals. Let's take a look at the eye diagram for both transmitted and the received one. So if you compare between the received and the transmitted signal through the eye diagram, we can see that the fiber propagation does not distort the transmitted pulse. So this way you can do the analysis.